Hello everyone. I will be presenting our paper in Winter Speech 2021. The title of our paper is Applying TDNN Architectures for Analyzing Duration Dependencies on Speech Emotion Recognition. The authors of this paper are Pooja, Kumawat and Aurobinda Routray from Indian Institute of Technology, Kharagpur. So first, I will briefly introduce the speech emotion recognition system. The speech emotion recognition, that is also known as SER, is the task to automatically recognize emotions from the speech signal. These days, there are various applications of SER system in human-computer interaction, smart speakers, and virtual assistants to understand their users in a better way. In this work, we would like to investigate how temporal information impacts the SER performance. Various literature studies lack in depth analysis and utilization of how emotions varies as a function of time. The psychological and neurological studies show that negative and positive emotions are not recognized at the same speed. Emotion recognition varies as a function of time, and this temporal process might change according to the kind of emotion. In our work, we address this issue of time dependencies and biases in SER tasks using TDNN architectures. There are three main objectives of our work. The first objective is to explore the ECAPA-TDNN architecture for speech motion recognition task and compare its performance with the widely used X-vector TDNN architecture. The second objective of our work is that for the trained TDNN model, analyze the training chunk length dependent bias on the overall SER performance by varying the test utterance duration. Third objective of our work is to investigate the performance correlation of the individual emotion classes with the variations of test utterance duration for the trained TDNN models. In this work, we have used three widely used emotional speech databases to train different TDNN models. These databases are RAVDESS database, Emo-DB database, and IEMOCAP database. This figure 1 shows the histogram plot of utterance durations for the audio files that are present in different databases. In our work, we have increased the amount of training data twofold by augmenting with additive white Gaussian noise. For this, we choose random SNR values in the range of 15 dB to 30 dB. Then after that, we have extracted the widely used 40-dimensional MFCC audio feature to implement SER system. To compute these features, we used humming window of size 20 millisecond with a constant frame shift of 10 millisecond. This is the ECAPA-TDNN architecture that we have shown in table 1. This architecture earlier outperformed the other TDNN-based architectures for speaker verification task. However, this architecture has not been explored in the emotion recognition field earlier. So we are interested for exploring its capability for SER task also. This slide shows the key highlights of ECAPA-TDNN architecture. In this architecture, in the pooling layer, channel-dependent attention is used to capture the global context during the pooling operation. The global context helps to utilize the important pattern information that is not present in the currently processed frame. In this architecture, one-dimensional squeeze excitation rest-to block, that is also known as SE block, is also introduced. The outputs from the shallower level SE block are concatenated and fed to the next layer, followed by the statistic pooling operation. Due to this multi-layer feature aggregation, the learned embeddings can carry more robust target-dependent information, whereas the original X-vector system only uses the feature map of the last frame layer for calculating the pooled statistic. The performance comparison of X-vector TDNN and ECAPA-TDNN architecture is given in table 2 in the terms of weighted accuracy and unweighted accuracy. From the table 2, we can observe that the ECAPA-TDNN model outperforms the X-vector TDNN for all three databases. So for the further analysis, we used ECAPA-TDNN architecture. Then we analyze the training chunk dependent bias on the overall SCI performance. For that, we trained the ECAPA-TDNN model with the different training chunk length for each of the three databases and tested with the different test utterance duration. All the results that we got, we have shown in figure 2. From figure 2, we observed that for most of the cases, the overall evaluation accuracy is maximum when the test utterances are of same duration as of the training chunk size. If the test utterance duration is decreased or increased from the training chunk duration, the accuracy value decreases gradually. We have also investigated the individual emotion class accuracy for different training chunks and testing chunks. Based on the previous analysis that we have done, the evaluation of varying test utterance duration are carried out with the models that are trained on the same training chunk lengths. From the results as shown in table 3, we observed that the prediction performance of certain emotion classes is more accurate only if the test utterances durations lies in a certain range. For example, for happy emotions in all the three databases, the prediction performance for the happy emotion increases if longer test utterances are presented to the ECAPA-TDNN model. Similarly, for the prediction performance of the neutral emotion in emotion class in Emo-DB and IEMOCAP databases does not vary significantly. In IEMOCAP database, the prediction performance of the said emotion degrades if the test utterance duration is increased from 2 seconds, whereas for angry emotion, the prediction performance improves gradually with the shorter utterance duration. As a concluding remark, in this work we have explored ECAPA-TDNN architecture for speech emotion recognition tasks and found it to be outperforming commonly used X vector architecture. Even though its overall accuracy is promising, we found two potential issues with it in the SCR task. The first issue lies with the predominant bias based on the training chunk duration of the models. And the second issue is that the individual emotion class accuracy is still very much dependent on the test utterance duration, even for the utterance level TDNN models. As a future research direction, we would like to mitigate the above mentioned two issues to make TDNN based SCR system more efficient. Thank you for your attention.